Assalamu alaikum. Welcome back to the lecture series for operating systems. I hope you are doing well. Let's start lecture 2. We are starting a new chapter called processes. Please refer to the third chapter of the William Stallings book for this topic. So, what is a process? A process is a program in execution. The program is a set of instructions stored on secondary storage. It is important to remember that execution of any entity can only take place after it has been loaded in primary storage. On the secondary storage, the program is a static entity because it cannot execute. When the user asks for a program to be executed, the operating system assigns an ID to it and creates some data structures for it, allocates a set of memory locations for the program in main memory, and loads the program code from the secondary storage to the primary storage. Memory locations allocated to a program are called its address space. Once the program has been allocated an address space in the primary storage, it becomes a dynamic entity as it can now execute. So a program becomes a process when the OS decides to execute it. What happens when a new student is admitted to ND? Number 1. He is given an ID card. This ID card has his seat number on it. It has his name and his department's name on it. It has other attributes of the student on it. Number 2. The student is shown a set of classrooms where all his classes are held. So he is given a place to stay when he is in the university. Consider this picture. There is a high-level language program which we typically save on the hard drive. When the OS decides to execute this program, it does two things. Number one, it creates an identity card for the process which contains the process's ID and all its attributes. This data structure is called the process control block or the PCB for short. Number two, the OS gives the program a place in the primary storage. This is where the program's variables and code will be kept. The PCB is also kept in this address space. As soon as the PCB is created for a program, it stops being static and turns into a dynamic entity, and we stop calling it a program and start calling it a process. So a process is actually a program to which the OS has promised execution. The creation of the PCB and the allocation of address space for a process are called housekeeping chores of the operating system. Before we go any further, let us try to answer this important question. When is a new process created? There are four scenarios that lead to process creation. New batch job. Suppose that an OS has been fed a batch of jobs. When the OS reads job control language or JCL commands that signal the start of a new job, it creates a process. Interactive logon. When a user logs into a terminal, the operating system creates a process for this user, created by operating system to provide a service. The operating system may create a process to provide a service to another process. For example, assume that I log into my computer. A process is created for me. Then I click on Microsoft Word. A process is created for this application. By clicking, I am asking the operating system to create a process. Now I open a file and click on Print. The operating system creates a process and assigns it the task of spooling or buffering the file to the printer. Please note that I have not asked for a process to be created, but the operating system has created this printing process for me so that my original Word process does not get tied up in spooling the file. While the printing process spools the file to the printer, my Word process is ready to take the next input from me, spawned by an existing process. A process can ask the operating system to create another process. The asking process becomes the parent, and the spawned process is called the child process. For example, I choose to edit a picture inserted in a Word document, and the Microsoft Word process spawns a process for Microsoft Paint in which I can edit my picture. The Microsoft Word process is the parent process, and the Microsoft Paint process is its child. This is the table that describes all four reasons of process creation. Let us now examine the reasons which lead to termination of a process. Normal completion means the process has executed all its code and finally terminates. Time limit exceeded means the process has run longer than the system-wide time limit. For example, there is a system in which the execution limit is 60 minutes. If the overall execution time of a process reaches 60 minutes, the process will be terminated. Time overrun means the process has been waiting for an event to occur longer than the system-wide time limit. For example, there is a system in which the waiting time limit is 30 minutes. If the waiting time of a process reaches 30 minutes, the process will be terminated. Memory unavailable means the process is asking for memory, but the system cannot complete this request, so the process is terminated. Bounds violation means the process is trying to access a memory location that it should not access, so the process is terminated. Protection error means the process is trying to access a file that it should not access, or it is trying to use a file improperly, such as trying to write to a read-only file, so the process is terminated. I/O failure means there is an error in I/O. For example, the file which was supposed to hold the input is not present, or there are bad sectors on secondary storage due to which read or write is affected, or the process is trying to read from a port to which the printer is attached. Of course, this is wrong because the process is trying to read from an output device. In case of I/O failure, the process is terminated. Arithmetic error means the same thing as math error in your calculator. You get this when you divide something by 0. It means the process is trying to do computation that is arithmetically wrong. When a process does this, it is terminated. Invalid instruction means the process is trying to execute an invalid opcode. This happens when the process mistakenly understands data to be instruction and tries to execute it and is finally terminated. Privileged instruction means a process tries to execute an instruction reserved only for the operating system. We talked about this in the previous lecture. If a process does so, it is terminated. Data misuse means the data being used is of the wrong type. For example, the process is fetching data from a location that contains a floating point number, but the process is using it considering it to be a character. The process is assuming the wrong type of data, so it will be terminated. Also, a process may fetch data from an uninitialized location that currently contains garbage. This is also data misuse. Finally, a process is terminated when the user tells the operating system to do so. You have done this many times by pressing Ctrl plus Alternate plus Delete, opening the task manager, highlighting a process, and then clicking End Task. In some operating systems, the system itself can terminate a process. This is operator or OS intervention. If the parent of a process is terminated, all its children are terminated because the children were created to serve the parent. So if a parent dies, all children die. If a parent process asks the OS to kill any of its children, the operating system does so. This may happen when the parent process has no further use of the child that it spawned. Here is the table showing all reasons of process termination. These reasons do not lead to termination in all operating systems. It is the discretion of the operating system designer to pick a subset of these reasons and implement process termination for them. What I intend to highlight is there is a chance that a reason mentioned here leads to process termination in my operating system, but it does not lead to process termination in an operating system designed by another person. Here I want you to pause the video and write the answers to these questions in a Word file. Task number 1. What is the difference between time limit exceeded and time overrun? Task number 2. What is the difference between invalid instruction and data misuse? See you on the other side. Now let us talk about the different states a process can have in the system. We will be talking about three models, one after the other: the two-state process model, the five-state process model, and the seven-state process model. Let us start with the two-state process model. Do you remember the concepts of multiprogramming and time sharing that we learned in the last lecture? Let us revise. Multiprogramming means there are more than one processes in the memory beside the OS. We are time sharing these processes. We make a queue and put the PCB of each process in this queue. At the head of the queue is the process that came first. The process coming last is at the end of the queue. There is an OS module called the dispatcher. The job of the dispatcher is to select a process from the queue and assign the processor to it. When the process is waiting in the queue, its state is not running. The dispatcher takes a process from the head of the queue, starts the timer for the time slot, and passes control of the processor to this process. Now the state of the process is running. The dispatch transition in the diagram shows the change of state from not running to running. The process copies its variables from its address space into the processor's registers. This is called restoring the context of the process. Then the process starts execution. When the time slot expires, the variables of the process are copied back to its address space. This is called saving the context of the process. The process is preempted, that is, the processor is taken away from it, and it is placed at the end of the queue. Now the state of the process is not running. The pause transition in the diagram indicates change of state from running to not running. If the process has not completed execution, it will wait in the queue until the dispatcher picks it up again. When it comes into the running state, it will start execution from the point where it was preempted last time. Saving and restoring the context enables the process to pick its execution from where it left the processor last time. When the process finishes execution, it relinquishes the processor or it gives the processor back to the dispatcher and leaves the system. This is indicated by the exit transition in the diagram. Some points are worth noting here. Number 1. Each slot in the queue contains a pointer to the PCB of a process. Number 2. When control is transferred to the process, its context is restored. That is, the OS copies the process variables from its address space into the processor's registers. Also, the OS reads the process PCB and sets the program counter to the address of the instruction to be executed. So, if the process executed instructions 1 to 4 in the first run, the OS would set the program counter to the location of the fifth instruction and continue execution in the second run. The last point is that when the time slot expires, the context of the process is saved by the operating system. That is, its variables are copied back from the processor's registers into its address space and the OS records the address of the last instruction executed in its PCB. So if the process was preempted after the fourth instruction, the OS would record the current contents of the program counter in the PCB to remember where it left execution. We saw that the queue is a round-robin FIFO queue. That is, a process is picked from the head of the queue and placed at the end of it when the time slot expires. Recall the general structure of a job, which consists of CPU bursts and IO bursts. This is a slide from lecture 1. A very important thing to note is this. A process executes when it is assigned the processor. A process can only ask for IO when it executes. This means that if a process is asking for IO, then it must be currently running. I always tell my students that only the one who runs has the ability to ask for something. Only the one who runs has the ability to ask for something. If a process is not running, then it can certainly not make a request. There is a problem with the two-state process model. Consider that a process is at the head of the queue. The dispatcher selects it and grants the processor to it. The job executes for a while and then asks for an IO operation. Then it relinquishes the processor. Control is transferred back to the dispatcher, which is a part of the operating system, and it places this job at the end of the queue. After some time, you will have two kinds of processes in the queue. Processes which are ready to execute and processes which are waiting for any IO event to occur. A process will not resume execution as long as the IO event it asked for is not complete. We call a process that is waiting for an IO event a blocked process. The OS records in its PCB the ID of the event it is waiting for. When the relevant I/O device completes its task, it interrupts the processor. This interrupt is inspected by the operating system. It determines which processes are waiting for this event. If necessary, it places the data from the I/O device in their address spaces, and it records in their PCBs that the event is complete. Now the dispatcher cannot simply pick a process from the head of the queue, because the process at the head of the queue may be a blocked process. The dispatcher must scan all PCBs starting from the head of the queue until it finds a process that is ready to execute. This increases delay at the dispatcher, and during this time the processor sits idle. So we dump the two-state process model and switch to the five-state process model. Here we use two queues. There is a ready queue which contains processes that are ready to execute, and there is a blocked queue which contains processes that are blocked for an I/O event. When a process is created, it is placed at the end of the ready queue. The dispatcher picks a process from the head of the ready queue and assigns it to the processor. When a process times out, it is placed at the end of the ready queue. During execution of a process, when it asks for I/O, the process is removed from the processor and placed in the blocked queue. When an I/O event occurs, the OS scans the blocked queue for all processes waiting for this event and places them at the end of the ready queue. A system can also use more than one blocked queues, one for each I/O event. In such a scenario, the OS takes all processes from the blocked queue of the event that just occurred and places them at the end of the ready queue. Now a process can be in one of five states in the system. A process is new when it is created due to one of the reasons of process creation. Its PCB has been created, but it has not been allocated an address space. Hence, it is not part of the pool of executable processes. When it is allocated space in the main memory, the process becomes executable and its state is ready. The state of a process is running when the processor is assigned to it. When a process finishes execution or when it is terminated due to one of the reasons of process termination, the OS deallocates its address space but keeps its PCB and other relevant data structures for some time for accounting processes. These processes gather statistics like total running time, total memory used, etc. So after completion of execution, a process is in the exit state. If a process asks for I/O during execution, the process leaves the processor and its state becomes blocked. Let us look at the transitions in the five-state process model. Admit: when the OS allocates main memory to a process, it transits from the new state to the ready state. The OS has now committed itself to the execution of the process. The process is now executable. Dispatch: when a process is allocated the processor, it transits from the ready state to the running state. If there is a single processor in a system, there can be only one running process in it. Release. If a process finishes execution or is terminated, it transits from the running state to the exit state. Timeout. When the time slot of the running process expires, the process transits from the running state to the ready state. Event wait. If the running process asks for an IO event, it transits from the running state to the blocked state. The running process calls the OS, asking it to get the IO operation performed. This call to the OS is called an operating system service call. Event occurs when interrupt arrives from an IO device signaling completion of IO event. The process waiting for it transits from the blocked state to the ready state. Two transitions are not shown here. One is from the ready state to the exit state. The other transition is from the blocked state to the exit state. These transitions can happen when the OS terminates a process and its child process is in the ready or blocked state. So essentially, it will be terminated along with its parent. These can also happen if the running process asks for termination of its child which is in the ready or blocked state. Pause the video again and write down the answer to this question. Task number 3. Consider a system with priorities. A high priority process named A is currently blocked. A low priority process named B is running. An interrupt signals completion of the event for which A is waiting. What should be the transitions in the system so that priorities are not violated? Here is another question for you. Task number 4. Consider a background process that executes for X nanoseconds, then sleeps for Y nanoseconds. It never terminates. Which transitions will it make according to the 5-state process model? We can further refine the 5-state process model to incorporate priorities. If the system enforces priorities, the dispatcher can have multiple ready queues, one for each priority level. A new process is admitted to the end of the ready queue corresponding to its priority level. The dispatcher always picks the process at the head of the ready queue corresponding to the highest priority level. The dispatcher switches to a low priority ready queue if all higher priority ready queues are empty. Please note that priorities can be enforced with a single ready queue as well. With a single ready queue in a priority driven system, the dispatcher will not be able to pick the next process from the head of the queue, but it will have to scan the whole queue for the process with the highest priority. This will increase dispatch delay. Multiple ready queues actually reduce this delay. In a multi-programming system, many processes are loaded in the main memory at the same time. If the currently running process makes an OS service call for IO, it is blocked, and another ready process is chosen for execution. Consider a scenario where all processes in the main memory are blocked. What will the OS do now to prevent the processor from sitting idle? If we try to increase the size of main memory, it costs us money. Also, programmers tend to write larger programs with each passing day, so this is not an adequate solution. The OS chooses one or more processes and swaps them out to the hard disk. All contents of their address space are copied to the hard disk. Then their address spaces in main memory are deallocated. Now main memory has room for more processes. The OS creates new processes and starts to execute them. A process swapped out to the hard disk is called a suspended process. It cannot execute as it is not loaded in the main memory. The suspended queue contains processes swapped out to disk. If an I/O event occurs, the OS marks the process blocked for it as ready. Afterwards, the OS may or may not swap it into the main memory, so a suspended queue may contain both blocked and ready processes. Swapping involves I/O, that is writing to or reading from the hard disk, so it always takes time. The more we swap processes in and out of memory, the slower the system becomes. Since disk I/O is generally the fastest I/O in the system, swapping mostly enhances performance by reducing processor idle time. Recall that a process becomes executable when all its code is loaded in the main memory. What happens when someone writes a program larger than the RAM in the system? This process can never be fully loaded in the main memory and can never be executed, which means that the size of the code is limited by the size of the main memory. To overcome this problem, we introduce the concept of virtual memory. Virtual memory is created by using part of the hard disk as an extension of the main memory. Keep in mind that we have lots of space on the hard disk. Now we tweak the condition for executability. We say that a process becomes executable when all its code is loaded in the virtual memory. Typically, all the process is loaded in the area of the hard disk that is mapped in virtual memory. The process is given a small address space in main memory. The process is divided into chunks called pages. The page currently being executed is loaded in the main memory. So the process is partially loaded in the main memory. When execution of this page completes, the OS swaps it out and swaps the next page into main memory. We can now execute programs larger than the size of RAM in the system. In a system using virtual memory, a suspended process is one which is only loaded on the hard disk and not even a single page is in the main memory. In this system, if a process has even one page loaded in the main memory, it is not considered suspended. If it is not waiting for an event, it is marked ready, otherwise blocked. There are 5 reasons why the OS may suspend a process. Swapping. The OS may suspend a process to free up memory. This memory would be allocated to another process. Other OS reason. The OS may suspend a background or utility program or a process that is causing a problem. Interactive user request. The user may ask the OS to suspend a process because the user wishes to debug it. Timing. If there is a process that works periodically, the OS may suspend it between successive runs. For example, a process activates after every 5 nanoseconds, does some work, then sleeps. The OS may suspend the process when it is sleeping. Parent process request. If the parent asks the OS to suspend its child, the OS complies. This is the table that describes all reasons for process suspension. Please note that a process is suspended by the operating system at the request of an agent. The agent can be the OS, the user, the parent process, or the process itself. If the process is suspended by the OS, the user, or its parent, it will be removed from suspension only when the requesting agent orders its activation. Finally, let's talk about the 7-state process model. A process can be in one of 7 states shown here. Let us talk about 4 of these states. A process is ready when it is in the primary storage, not waiting for any event. A process is blocked when it is in the primary storage, waiting for an IO event. A process is ready suspended when it is in the secondary storage, not waiting for any event. A process is blocked suspended when it is in the secondary storage, waiting for an IO event. The definitions of the rest of the states remain as they were in the 5-state process model. There are 2 new queues in the 7-state process model: ready suspend and blocked suspend. Let us look at the transitions taking place in the 7-state process model. When a process is created, the OS has 2 choices. The OS can immediately allocate address space to it in the main memory. In this case, an admit transition takes place from new to ready. But if the OS is running low on main memory, it may choose to create the process, make its PCB, but not allocate main memory to it. In this case, the process is loaded on the hard disk only. This results in an admit transition from new to ready suspend. The dispatch, timeout, event wait, and release transitions have the same meanings that they had in the 5-state process model. When the OS allocates main memory to a ready process currently on hard disk, the activate transition takes place from ready suspend to ready. When the OS allocates main memory to a blocked process currently on hard disk, the activate transition takes place from blocked suspend to blocked. At first, it makes no sense. Why would the OS activate a blocked suspended process? Consider this scenario. The blocked suspended process has a higher priority than all the ready and ready suspended processes, and the OS has reason to believe that it will be unblocking soon. In this case, the OS brings it into main memory so that it can join the ready processes as soon as it unblocks. The OS may swap a blocked process out of main memory to the hard disk. This is the suspend transition from blocked to blocked suspend. The OS may do so to free up memory, which it may give to another process. The OS may swap a ready process out of main memory to the hard disk. This is the suspend transition from ready to ready suspend. At first, it makes no sense. Why would the OS suspend a ready process? Consider this scenario. The OS needs memory. There are only ready processes in the main memory. The OS will choose the lowest priority ready process and swap it out, freeing up memory. Another scenario to consider is this. There is a blocked process in the main memory, but it is of high priority and the OS believes it will be unblocking soon. So the OS swaps a low priority ready process instead of the blocked process. If an IO event occurs, the process waiting for it in the main memory transits from blocked to ready state. If the waiting process is on the hard disk, it transits from blocked suspend to ready suspend state. Now consider that all the primary storage is full of processes and there is no free memory. The highest priority process named A is in the blocked suspend state. Then the IO event it was waiting for occurs. If priority is to remain untempered, A has the right to run. The OS preempts the running process named B because it is lower in priority and then swaps it out on the hard disk. This frees up memory which the OS gives to A. Not only that, the OS gives the processor to A too. B has just been dealt a double blow and it experiences the suspend transition from running to ready suspend state. Finally, a process can transit from any state to the exit state. This happens due to parent termination or parent request. These transitions are not shown here. In this lecture, we introduced the concept of a process. A process is a program in execution. We saw the reasons due to which a new process is created and the reasons which can lead to its termination. We introduced the concept of virtual memory and suspension. We traced the life of a process from birth to death and explored the different states that it can have in an operating system. What I want you to do now is read the book and the relevant chapter. I will ask you to submit the Word file saved as your roll number lecture 2 via Google Classroom. Write your questions on a piece of paper and keep it in front of you during the online session. If you have suggestions relevant to content or quality of this lecture, email them to me. I will see you again in the next lecture. Allah Hafiz.